So I am going to, well, first let me number these. So there's body 1, there's body 2. And when I do body 2, I am going to isolate what the? I don't know. It just like, sometimes it makes wild assumptions about what I'm trying to draw. Okay, so I'm going to isolate something like that when I get to body 2. So body 2 is going to include that pulley that's attached to it. Okay. Can anyone put words to why I'm choosing that? Why am I choosing to deal with the pulley that way? Yes. Yeah, and if I just did it like, if I cut it off here, notice that that's a fixed joint between the base of that pulley and this thing, you know? So that would be, in that case, I would have a full force vector and a couple acting. That's 3 variables I would introduce, okay? Doing it this way, the only variable I introduce is that cable tension, okay? So by doing this, I cut out 2 variables out of my system. Not that you couldn't do it the other way and then go back and isolate a new thing. You always can, work around and finally solve your system. But this is going to get us the quickest set of answers to what we're trying to find. Okay, so free body diagram question?
Yeah, in the right, there's still one tension.
Yep.
Do we count this too?
Yes, that's right. So I'll be more clear when I draw the free body diagram, but the main tricky thing in this problem is coming up with a good way to approach that pulley system. So free body diagram of body 1. There's a fixed joint down here, so we have a full force vector. I'll call these joints A, B, and A, B. I guess those are the only joints, aren't they? So we have 5,000 here. I think I haven't said yet, but I guess I'll probably do it down here. Just makes the geometry a little simpler for me to think about.
You don't have a moment down there?
You're right. Yep, you're totally right. That should have a moment because it's a fixed joint. Yep. And there are no weights on this thing. So the only other force is up here, the force on 1/2. So rho, force, moment. The force RA, the rho vector is 0. The force is RAX, RAY. Cross product is 0. And then MA, that's the couple. We don't care about these things for couples, and we just have MA. And then the 500, that is 0.25 meters up from the about point. So 0.25. Force vector is 5,000, 0. And so the cross product is negative 1250. and then F12. The row vector is 0.5. Force is F12x, F12y. Cross product is negative 0.5 F12x. And so equation 1 says RAX plus F12x is equal to negative 5,000. Equation 2 says RAY plus F12y is equal to 0. And equation 3 says MA minus 0.5 F12x is equal to positive 1250. Any questions about the first body? And now body 2. I'll sort of think of like this. You follow all the stuff I'm drawing on that. So we have a downward force of 15,000 on the left. At the middle, we have negative F12. And now you can see that the only force acting here is the cable, acting on the cable. That's clearly a tension force. Over here, it's a cable tension force. That's all the same cable, just going through pulleys. So that is T, T, T. And there's nothing else acting there. I guess I'll put my about point at the midpoint.
Do you have like rotation?
A moment.
Yeah, in F12.
Nope, because the difference is down here at A, that's a fixed joint connected to the ground. Here, that's a pin joint. Yeah. Okay, 0.8, 0.6, 0.2. There is one thing that isn't in here that you would very reasonably think is going to matter here, and that's the radius of that pulley. I'm going to put it in, I'm going to treat that pulley radius like it's R. What you're going to see is that the R's cancel out and it doesn't end up mattering what the radius of that pulley is. But, okay, so for the 15,000, the row vector is negative 0.80. The force vector is 0, negative 15,000. The cross product is positive 12,000. Then negative F12. Row vector is 0. Force is negative F12x, negative F12y. Cross product is 0. Then I'll do the T on the left, the leftmost T. The row vector is, so that is going to be, for the x component, that's going to be 0.6 minus the radius of that pulley. We could also represent the height of that force as like a variable h or something. But look at the line of action of all of those cable forces. They're up and down, so that height isn't going to matter. You can move the location anywhere along its line of action. Okay.
Why are you subtracting minus r?
Because that force really is, so it's 0.6 to here, but then it's 1 radius to the left of that.
Oh,
Okay. But what we're going to see is that those r's cancel out. Okay.
So the other one will be 0.6 plus r.
The other one's going to be 0.6 plus r. Yep, exactly.
If we knew the radius of the pulley, then that would.
Yeah, if we knew the radius was 0.1, then we could just call it 0.5. Yep. And then the force is 0, negative t. And so the cross product is negative 0.6 t plus rt. And then the t in the middle, that is a row vector of 0.6 plus r. And then I'll just use 0 for the y component. The force vector is 0, negative t. Cross product is negative 0.6 t minus rt. And now if you look at, how those r's appear in the moment equation, you can see that when we do the in the moment equation, the rt and the negative rt are going to offset each other, and it turns out r doesn't matter. We could have just treated those like they both acted right at the center of the pulley, but this is a more careful way to think about it. And then t on the right, that is at 0.8. And then I'll treat the y component like 0, 0, negative t. And so we have negative 0.8 t. And so equation 4 says negative f12x is equal to 0. Equation 5 says negative f12y minus t minus t minus t, I'll just write that as minus 3t, is equal to 15,000. And equation 6 says negative 0.6 minus 0.6 minus 0.8 is just 2. So that says negative 2t, the RT and the negative RT cancel out, is equal to negative 12,000. And this one looks like it wouldn't be too bad to solve by hand. You can just right away see that T is 6,000. Then you can plug that in here and get F12Y is 3,000, and then sort of unravel it piece by piece, it looks like. Or you could put it in a matrix. Any other questions about that one? Yep. Okay. Another one?
not solving anything, it's just a question because I'm adding something different. But for number 7, we're given the length of the vertical beam be 1.5, but on your answer you have like 1.4 something for the the row vector.
Okay.
Would it be okay to still have 1.5, or would you need that 1.5?
There's two possibilities. One, I made a mistake, and then the other one is that that my about point was the top, and then it looks like, because this is a 45, 45, 90 triangle, this distance is 1.41.
Yeah, it is. Yeah.
So
Okay.
if my about point was there, then that would have been down 1.4, whatever.
And for when you, like at the bottom, like if you go, like from the top to the bottom, then that would just be 1.5.
Yeah, let's do this one. This looks like, what would you use this for? I think the most effective use of this thing is to break itself, it looks like. And I think that would be it would be pretty good at that probably.
Handle. You know the one from the window that you grab onto.
Uh-huh. Huh.
Stuff.
That's funny. You could use it as like a nutcracker.
It looks like a polygon structure.
Uh-huh. Okay. So I'm going to call, we only have 2 bodies on this. I'll call this one body 1 and the T-shaped thing body 2. Also, let me move that number I just drew for a second, put it up here. What if you wanted to figure out how likely it was for this body 2 to break here? How would you go about doing that? Well, one thing you could do is think of this as 2 separate bodies that are joined by a fixed joint, and then you would actually calculate the forces and the couple that are required to keep these things from breaking, and based on that, then you could say like, okay, that weld joint there, whatever that connects those 2 things can or can't withstand that load. That is really the principle of internal loads, which is one of the next topics we're going to go into. Okay, so it's like where you want to figure out if something's going to break, you just imagine that, you just separate your 2 bodies at that joint, and then you calculate the forces and couples required to hold them together. Okay, so that's a principle that's coming up soon. And I'll call this A, B, and then C. So free body diagram of body 1. We have a force RA. This is a fixed joint, so we have a couple MA. Where the roller touches the body. So the rule for a roller force is perpendicular to the surface of contact toward the chosen body. So that force is going to be like this. I'll call that RC. And then up here, we have the force on body 1 by body 2. And the reason I didn't, so that RC is also a force on body 1 by body 2, but I didn't use that double subscript notation on that because that is not a force vector. That is a force with a known direction. Okay, that double subscript notation only works for force vector components. Okay, and so we'll see how this comes out when we get to body 2. This, which one?
The RC.
Yeah, that is because that is a force with a known direction.
Oh,
It's because that's a roller instead of a pin joint, you know?
oh, yeah. So we don't-
And so instead I drew the direction of the force and just gave it a scalar, single number variable name. Okay, so rho, force, moment, and I'm going to make this my about point just because I know that that distance is square root of 2. Come on. Okay, so the force F12, rho vector is zeros. Force is F12x, F12y. Cross product is 0. Then the force RC, that rho vector is 0, negative 1.414. Yeah. The force vector is negative RC 0. Cross product is negative 1.414 RC. Well, it's 0 times 0 minus this times this, so minus a positive. And then last is, well, no, there's 2 more. RA, the rho vector is 0, negative 1.5. Force vector is RAX, RAY. Cross product is positive 1.5 RAX. And then the couple. So that is MA. Equation 1 says F12x minus RC plus RAX is equal to 0. Equation 2 says F12y plus RAY is equal to 0. And equation 3 says negative 1.414 RC plus 1.5 RAX plus MA is equal to 0. Any questions about that body? And then body 2. Here we have F12 negative, force on 2 by 1. 2000 up at the top right. And now when you have forces with known directions acting between two bodies, you can keep the same variable name and just switch the direction. So this is going to be RC going this way. So rho, force, moment. I'll put my about point here. So first negative F12 has a rho vector of 0. Force vector is negative F12x, negative F12y. Cross product is 0. This is just, so that is just going to be a rho vector for that top point. So the 2000 Newton force just has a rho vector of positive 1.4140. Force vector is 0, negative 2000. Cross product is negative 2828. And then the force RC, that has a rho vector of 0, negative 1.414. Force vector of RC 0. Cross product is 1.414 RC. So equation 4 says negative F12x plus RC is equal to 0. Equation 5 says negative F12y is equal to 2000. And equation 6 says 1.414 RC is equal to positive 2828. I guess let's get answers for that. So equations 1, 2, 3, 4, 5, 6. And we have RAX, RAY, F12X, F12Y, MA, RC, and the constant. Okay, so for equation 1, F12X, we have 1. Then RC, negative 1, and RAX, 1. Then equation 2, F12Y plus RAY. So 1 here, 1 here. And then equation 3, RC is negative 1.414. RAX is 1.5. MA is 1. Equation 4, F12X is negative 1. RC is 1. Equation 5, F12Y is negative 1. The constant is 2000. And then equation 6, RC is 1.414. The constant is 2828. And I got RA is 0, 2000. F12 is 2000, negative 2000. MA is 2828. That's Newton meters. And RC is 2000. Any questions about that?
In the frequent diagram number 1.
Yeah.
Did you find RC, the Roberto Blackie?
Whoops. How did I know to put it like that?
No. How do you know that it was negative 1.414?
Oh, yeah. Well, this triangle, oh my God, come on. So this triangle, 45 degrees here, 45 degrees here. You could break it as 2 right triangles like this. That's 1, 1, no. 1 here, 1 here. And so now if you can use trig and you get that this is 0.707. This is 0.707. This is 0.707.
Could you go down?
Yeah. Any other questions on that one? So the thing you don't have to do on a ton of these problems is put in forces where you know the direction, but you don't know the magnitude. So that was the only thing different with this one, is how to treat that roller that's inside the structure, Most of the time, those rollers in structures appear only in contact with the ground or the wall or whatever. Okay, but just follow the rules for what a roller does. And then when you go to the other body, remember that anytime you represent a force as a known direction and an unknown magnitude, when you go to the other body in the contacting pair, keep the same variable and just switch the direction to the opposite direction. Any other questions about that? Okay, that's all. I have 2 more of these problems to give you. So, and don't worry, they'll get a little harder.